Hello there, welcome to another tutorial. Okay, the binomial pricing model has two important components. These two components are a model for how the stock price changes over time and a model for the value of a riskless bond changing over time. So the first thing we need to do is to decide how we're going to represent time in this model. And one way to do this is to consider a single time step of size delta t. So we consider time changing from a current time t to a new time t plus delta t. And then we build a model in two parts. We build a model for cash invested, or equivalently a riskless bond. So a cash or riskless bond investment, assuming no arbitrage and assuming continuous compounding at interest rate R, an initial amount B invested will grow over this time interval of size delta t to be b e to the r delta t. Remember, because we're moving forward by one time step here, the power on this exponential is positive. The cash investment, or the riskless bond, is earning interest, so growing in size. We're not discounting back from a future value at this point, so we don't have a negative power here, it's a positive power. So the second component of the model that we want to build is a model for how the stock price changes. So we'll suppose that we're given some stock price st at time little t, and we build a very highly simplified model of what the stock price can do. We consider that there are only two possibilities for the stock. It moves up or down by a fixed factor each time. So if the stock moves up, we multiply by a factor u to get ust, which I'm going to call stock up. Or if it goes down, then we multiply by a factor d to get stock down. So the idea here is, in order for this to make sense, obviously we would like that the down factor lies between 0 and 1 and the up factor is greater than 1. And we choose one of these possibilities according to different probabilities. So we'll choose the up case with probability p and the down case with probability 1 minus p. So these are the only two possible scenarios that we're going to consider. So here's our model for time, the bond and the stock. Now, what is the point of the binomial pricing model? What we want to get out of this is the theoretical option price. So we have this model for the stock price with these two future scenarios, so we just augment our model now by making a model for the option price. So in a very similar way, we have one scenario now and we have two possible future scenarios. So we need to consider how the option looks in these three different scenarios. So in the present day, the option value must be Vt, and in the future scenarios I'm going to denote the option values V up and V down, and the probabilities must be the same as those here. Okay, now how can we make progress figuring out the option price? Well, if this future time step here was the expiry time of the option, so if this were actually time capital T, expiry, then at least for non-path dependent options, we could figure out the payoff function for the option in both of these two cases. So if I just write down an example here, if we had a call option on the stock, then the payoff at the end here would be the maximum of the final stock price minus the exercise price with 0. So that's just the example of a call here. And we would only be able to write down that formula if this final time step was the expiry time. Now similarly for the call on the down step, we could also write down exactly what the option price should be at expiry. And the thing that we want to find out here is the option price one step before. So in this case, Vt is the thing that we actually want to find. Okay, so we've built our binomial model for the cash, the stock and the option, and now we want to figure out if we can find an expression for this present day option price under assumptions like no arbitrage. So let's do that. So the big idea, or one of the big ideas in modern finance, is what are called replicating portfolios. So what does this mean? Well, a portfolio replicates an option if it takes the same value that the option does in various different scenarios. So let's see what we can do here. The idea is that we're going to build a special portfolio, and we're going to build it out of some units of the stock and some units of cash, or the riskless bond. Okay, and the idea is that we're going to choose these two variables, phi and size, so that we get the correct payoff for the option in the future. So we want to choose these two numbers so that our portfolio value matches the option value. In particular, that it matches it at expiry time. Under the assumption of no arbitrage, if the future portfolio value is equivalent to the future option value, then it must be, again under no arbitrage, that today's portfolio is worth the same as today's option. Okay, so that's the idea behind this trick. Now let's see if we can actually do it. Let's figure out what the portfolio would be worth. So let's look at the position today, which I'm going to take as time t, and the idea is that we're going to invest in a certain number of units of stock and some other number of units of our riskless bond position. So let's figure out what the portfolio itself is worth today. If I let capital pi represent the portfolio, so pi for portfolio, then its value today, pi subscript t, must be, well, we have this many units of the stock today plus this many units of the bond today. So there's our equation for today's value of the portfolio. Now what about the future value of the portfolio? So supposing that we just hold on to this portfolio and we don't trade in and out of it, then its value one time step ahead at time t plus delta t is, well, let's figure out what's happening here. We're holding the stock, and if we hold the constant number of units of the stock, then it's just the stock price which changes. And what about the bond? If we're holding the same number of units of the bond, so we haven't traded in or out of our position, then we just have the new price of the bond after it's earned interest forward in time. Our investment has grown. So this is the future value of our portfolio, and now the trick here is to get this expression to match the two possible future values of the option. So basically what we want to do here is to choose our two constants so that in all possible scenarios our portfolio value here matches our option value. The portfolio value in the future is the same as the option value in the future. But our option value in the future takes two possible values, V up and V down. So we need to get our portfolio to match both of these possibilities. So let's look at the possibilities in turn. So the first is the up scenario, where the stock price moves up. Now in this scenario, the future stock value is the up value, S up. So in this case, let's see what we get. So our future portfolio value on the left has got to be equal to our option value. Okay, so that gives us one equation in two unknowns here. What about the down scenario? Well, it's very similar. So in the down scenario, the stock price has moved to DST, which we've called S down. And again, let's write out the value of the portfolio, and we want this to match the value of the option. So if we can manage to choose these two constants so that we do produce the correct option payoffs, then we've made a replicating portfolio. So it replicates, in other words, it reproduces the same behavior as the option price at the future time. Well, there's some hope here that we might be able to do this because we've got two unknowns and we've got two equations. So let's just label these equations. So I've called them 1 and 2, and now we can manipulate these in order to try to figure out the unknowns. Okay, so here are our two equations and our two unknowns. Now the simplest thing we could do here is to subtract one equation from the other, since we have this common term here, the riskless bond term. It doesn't particularly matter which order we do this in, but I'm going to do equation 1 minus equation 2. So I'm going to call this equation 3, and we can note straight away by rearranging equation 3 that our stock position should be the difference between the possible future option prices divided by the difference between the future stock prices. Now, for those of you who've already looked into the Black-Scholes proof and the definitions of the Greeks, you'll recognize this straight away as being an approximation to the delta of the option, because we've got a change in option value with respect to a change in the underlying stock value. And we shouldn't be too surprised by this. If you know something about hedging, you would expect this to come out to be the hedge factor. Okay, so what about finding the riskless bond position that we need to take initially? Well, now that we have this hedge factor here for the stock, we could plug this into either of our equations and rearrange in order to find the riskless bond factor. So I'm going to plug this into equation 1, and then let's see what we get. So firstly, all I've done is to rearrange equation number 1, and now I'm going to perform the substitution. Okay, so I've substituted in there. This doesn't look like a particularly enlightening expression, but we will now be able to collect some terms together. Okay, so at this point we've derived expressions for the number of units that we want to initially invest in the stock and the number of units that we want to invest in the riskless bond position. Now I want to do a little bit of simplification here, just to see if we can get some nicer expressions out for these quantities. So there are a number of things that we could do here. Our initial bond position B, we could choose that to be 1 unit of currency. The second thing I want to do is to see if we can simplify these expressions involving S up and S down, because we have some information about S up and S down in our model. So let's just recall that S up is US and S down is DS. So we could plug that information in too, and in fact that's what I want to do first. So let's go back to our expression for the number of units to be invested in the stock, and we can simplify that as indicated. Okay, so now let's do the same for the expression for the number of units to be invested in the riskless bond position. So I'm going to do two things. I'll set B equal to 1, which will eliminate B here, and I'm then going to divide through by this exponential factor. Okay, so what I've done there is to collect substitute in the S up and S down factors and then collect, and you'll notice something interesting here. The stock value here cancels out. Okay, so what have we achieved so far? We now know how to build a portfolio. So our portfolio consists of a certain number of units of the stock and another number of units of our riskless bond position, so such that our future portfolio value is equal to our future option value in all of the possible scenarios. So this is our portfolio value in the future, that's one time step ahead, and that's equal to our option value in the future. So now here's the clever bit. If we assume that there are no arbitrage opportunities, then the fact that we know how to build a portfolio today that will become worth the same as the option in the future means that they must have the same value today. So under no arbitrage, today's value of the portfolio is equal to today's value of the option. And note that today's value of the option is the thing that we always wanted to find out. So our portfolio today is worth the same as the option today. Okay, so we know that today's value of the option is equal to today's value of our portfolio, and we can figure out today's value of our portfolio because we now know what these constants are up here. So let's do that. So today's option value, the thing we want to calculate, is the same as today's portfolio value. But today's portfolio value was, well, we had a certain number of units of stock today plus a certain number of units invested in a riskless bond position today worth 1 unit of currency. So now we can plug in the two values for these constants from our earlier calculation and figure out the value of the option today. Okay, so all I've done here is substituted in the values that we'd already calculated for our two constants. And notice that immediately we can cancel the asset price again. So it now remains to tidy this up a bit and see if we can collect terms in a meaningful way. So the first step I'm going to take in trying to clean this up is to notice one very interesting thing that's come out of the calculation so far. The quantity e to the minus r delta t is the discount factor, which discounts a value backwards in time by the time step size delta t. So why is this interesting? Well, we're talking about today's option value, and on the right hand side we have lots of future option values, but we also have the discount factor that discounts back from the future time to today. So a natural way to write this out would be to put this discount factor in front of everything. So we're expressing today's price as a discounted combination of future prices. That seems like a very natural thing to do. So let's just do that using algebra and see what we get out of the front of these expressions, and then I want to combine them together afterwards. Now this expression here, this term, didn't have e to the minus r delta t in it, so in order for this to work I'm going to have to multiply that one by e to the plus r delta t in order to compensate. So there's our first term. Now the second term already had this factor e to the minus r delta t in front, so it remains to simply copy down the remaining parts. Okay, so now what I want to do is to collect things in terms of the future prices. So I'm writing today's price as a discounted combination of future prices in here. So let's bring out all of the future prices to make this relationship obvious. So what I want to do inside this bracket is to pull out all of the terms that involve the up option price and all of the terms that involve the future down option price. Okay, let's look at all of the places that the option up factor occurs on the left. Okay, so I've collected the down factors now, and again we see this common denominator u minus d, so it looks really natural that we simply collect everything over the common denominator. So firstly, I've put this fraction here over the common denominator u minus d, and notice that when I do so, there's a cancellation. So already we've simplified this into something a lot nicer. Let's see what happens now with the bottom term. So also the bottom term seems to have simplified into something a lot nicer. Now it's not necessarily obvious to see this, but actually this factor in the bracket here is 1 minus this factor up here. So I'm just going to illustrate that. If I let q be this quantity on the top here, e to the plus r delta t minus down factor over up minus down factor, and then look at what we get if we calculate 1 minus q. So 1 minus q is up minus down over up minus down. That gives us the 1 minus q is subtracting away this, so we have opposite signs on the top than we did before. And notice that another convenient cancellation takes place. Minus down factor plus down factor. So something quite remarkable has happened. Let me collect the terms together and show you why. So expressing everything in terms of this new quantity q, we get the following expression. So let's clarify what we mean here. We have the option value today is a discounted combination of the future option values. But notice the form of this combination, in which the weights add up to 1. So we have q lots of v up and 1 minus q lots of v down. Well, if q were a probability, then this expression would be the expected future value. So this is very interesting. Provided we choose q as our probability of an up move instead of our original probability p, then we can write this whole thing as an expected future value. Okay, so let's introduce some notation to make this a bit more concise. So we have our option value today is a discounted back to today expected future value. However, where the expectation is taken according to this new choice of probabilities q and 1 minus q instead of our original probabilities p and 1 minus p. So this is a remarkable observation. It turns out that there are some fairly deep reasons why this is true, all to do with this changing of the choice of probabilities q. Incidentally, this assignment of probabilities of q and 1 minus q is what's called the risk-neutral measure, and q is called the risk-neutral probability. Okay, well, thank you for watching. In this tutorial I've demonstrated how, by taking the very simple one-step binomial model, we can express today's option value as a discounted combination of expected future values, provided that we move from our true probabilities to what's called the risk-neutral probabilities, q and 1 minus q. Thanks very much for watching, and enjoy Math for Finance.